Friday will be a
Looking around for anything. So she would just wait. There means the face, tie raising again.
Good morning, everyone. I'll wait a minute or two before we get started. I feel like the number of students in the classroom is significantly less than it was last week, which is no surprise. The weather's awful out there. So I really appreciate those of you that are here. And those of you that are joining online, appreciate that you're joining online also. Yes, I've been reduced to carrying my own Crocs to the classroom, which I'm now going to put in sport mode so that I don't trip on myself. But I can't walk around for 3 hours lecturing in those Frankenstein boots.
Yeah, same.
Okay, good morning again. I recognize there's probably still a few people getting situated, so I'll kind of ease into things a little bit with some announcements. Today's class, I anticipate, will probably end around 12 o'clock, so I'm going to do my best to keep us on schedule. If I am efficient with my words, we might even be able to finish up around 11:55. So that's my goal. So let's get into some of our discussion. First, some announcements. I looked at what the foggiest concepts, and there's not a whole lot. Somebody did ask why I always use squash as an example. Do squashes help with encoding? Someone else pointed out once that there's about 20 occurrences of references to squash in the textbook. I guess I was really into squash when I wrote it. I don't know. It just comes up. So again, today we will use squash as an example, but I'll try to use some other things too. Somebody did have a question about the Craik and Tulving study and how are different levels of processing different from attention and inattention? Well, that's a really good question. Different levels of processing refer to where you place your attention, more so than attention versus inattention. So attending to something means that you are putting some mental resources towards it and working to try to encode something. In Craik and Tulving's study, they changed the focus of where your attention was. So everybody was paying attention to something. If you were in the structural condition, you're paying attention to the form of the letters. And if you're in the semantic condition, you're paying attention to the meaning of the words. So it depends where your attention is placed. And correspondingly, you then remember what you were paying attention to. Those individuals who paid attention to the structural aspects likely encoded information about the structural aspect. People who paid attention to the meaning encoded more about the meaning of the words, which meant that when they were trying to remember the list of words later on, they performed better. Another question here, textbook mentions properties of memories in attention, incidental, effortful, non-effortful, explicit, implicit. These seem like overlapping constructs. They are overlapping constructs. And so some of them have to do with the ways they've been described in the literature in different ways. In other cases, it has to do with encoding versus processing versus retrieval. So effortful versus non-effortful is a distinction that usually refers to the encoding process, putting effort into encoding something versus putting no effort into encoding something. Implicit versus explicit can mean that, but could also refer to how the information is retrieved. So implicit retrieval in memory means that you're not aware that your memory is influencing your judgments. So when we've talked about some of the heuristics and the biases availability and representativeness, for example. You may be aware that your memories are influencing your decisions, or you may not be aware that your memories are influencing your decisions, and that might be more of an implicit retrieval. Does that help a little bit? Okay, so those were the two questions that I found. Somebody wanted to know about squash. I have no idea. I guess it just sort of worked out that way. Okay, so a little bit more review. I'm going to go ahead and let's see. I should start my billable hours to see what I can do. I was going to try to hide the floating meeting controls. There we go. So far, let me just back up over several classes. Class number 2, unit 2, was all about similarity. And I said that similarity is going to underlie a lot of the other kinds of thinking processes that we talk about. So things are recognized and grouped together because they're similar to each other. And we talked about lots of ways in which similarity can be measured, assessed, and represented in a system. So similarity is important. Then we talk about memory. So memories are held together by similarity. Memory influences your decisions. It influences your problem solving and your reasoning. Memory works by allowing present events, what's happening now, to activate previously experienced events as a function of similarity. So we're trying to build up a system of thinking where we understand how things are held together mentally by similarity. So concepts that are similar to each other, ideas that are similar to each other are going to recall in a similar way. So you think about one event, it's going to activate events that are similar to it. That's going to have impacts for your memory and how your memory is going to influence decisions and problems. Today, I want to go just a little bit further. We'll do a little bit more review. But what we're going to talk about today is to build on that. We're going to talk about memory structures. So we talked about the memory process, encoding and storage and retrieval. We talked about short-term memories and long-term memories, episodic, implicit, and so on. Today, I want to talk about concepts and categories, which are a type of memory representation that encodes your knowledge. So this is a structure or a structured memory representation that can really be useful in how you think about that. Am I on here? So this is what we talked about last week. So we talked about input, again, similarity, short-term working memory, activating long-term, declarative, episodic, and semantic, and all of these things influencing your thinking process. So this all seemed fairly straightforward. This is all some pretty high-level review. We also talked about the ways in which memory doesn't work properly. We talked about all of these memory errors. And a lot of them, one of the things they have in common is that you remember things, but you don't remember the right things, or you don't remember them in the right way. So you might be suggestible. When people tell you something about your memory, you might recall it differently. If people ask you about something in a particular way, that influences the memory itself. So these 7 sins, transience, absent-mindedness, blocking, misattention, suggestibility, bias, and persistence, they all have something to do with the ways in which your memory lets you down. At the end of the class, I talked about how memory errors are usually just a function of the way your memory works. So it doesn't mean that you're making mistakes, that you should be blamed if your memory doesn't work. Your memory works that way because that's how it's designed. It's how it was evolved. Mostly these kinds of heuristics and biases that we're prey to are a function of your memory working right. So availability is usually going to give you the right answer. Representativeness is usually a quick way to come up with the right information. Occasionally it's wrong. And so that's what we'll continue to focus on today as well. So thinking, or these are, again, review, and then we'll move into concepts. Thinking or executing a behavior based on the first similar example that comes to mind is one way to describe an availability heuristic. So availability means that memories are available to you. And you use the ease with which you can remember those things as a cue to whether or not it's the correct information. If you can remember it really easily, if it comes to mind quickly because it's similar to what you're dealing with, then it's likely going to be interpreted by you as the correct information. And usually it will be the correct information, which is why it's a helpful heuristic. It's only a bias or an error when it's the incorrect information. We also talked about representativeness, like a typical farmer or a typical librarian or a typical liberal, typical conservative, any of these types of things which might be considered as typical. Reasoning from memory of a prototypical example, something that seems like the most common or the most prototypical or the most familiar example. What do you think of when you think of someone who has conservative opinions? What do you think of when you think of someone who is a librarian? You might activate particular characteristics. And if you assume that everybody who's in that category has the same characteristics, what you're doing is reasoning on the basis of representativeness. A single person that you might know who is a member of this category has particular attributes. And if you assume that everybody in that category has the same attributes as that single person you might bring to mind, then that's an example of representativeness. You're assuming that everybody has those same features. That one person is representative of everybody in the category or everything in the category. So that's why I want to focus today on concepts and categories, because concepts and categories are one way to think about how we represent information. So categories and concepts. So I always start off with this example, and I talk about this in the textbook as well, because I think it's a really good example of how one object or a thing can belong to multiple categories, depending on what kind of information you need. So what you should think when you see this particular, when you see Tylenol, is you might activate the concept of medication or the concept of drugs or pharmaceuticals, right? So when you think of taking a medication, what are some of the other concepts that come to mind? When do you take Tylenol, for example?
Pain relief.
Pain relief. I feel like every morning I wake up and I look outside. I need some pain relief, right? So Tylenol is good for pain relief. What else do you take Tylenol for? If you're sick, so you get a fever, it could be a fever reducer. So it can reduce pain, it can reduce inflammation, it can be used to reduce side effects of infection, like a fever. So it's pretty general purpose medication. And another thing that most people might activate a concept of medication is that it usually makes you feel better. It's a thing that is used to improve your situation. If you have a headache now, and you take Tylenol, you assume that in 30 minutes or so, you will have less of a headache. If you have a fever now and you take Tylenol, in about 30 minutes, you'll have less of a fever, right? So it's a thing that would normally be associated with a positive outcome. And in fact, that's how it usually has been branded. Now, this is an old advertisement. And the reason I like this old advertisement is that it highlights how Tylenol in particular, acetaminophen, was marketed to consumers in the 1970s and the 1980s. It was recommended as being why doctors recommend Tylenol more than all leading aspirin brands combined. Now, does anybody actually take actual aspirin for anything? Most people don't take aspirin for anything. In the 1970s and 1980s, it would have been referred to as kind of the generic term for pain relief. So I think, I don't know what term you use generically, but I kind of just use ibuprofen or Motrin. Even though Motrin's a brand name, right? I might just say, well, I'm just taking Motrin. Give me 2 Motrins. And I don't care what brand name it is. Of course, I'm going to buy Shoppers Drug or Rexall brand. I'm not going to buy the name brand. But when I say Motrin, I mean a ibuprofen type pain reliever. So aspirin would be the same thing. It's a particular kind of pain reliever, but in the 70s and 80s, it was just kind of the generic term as well. And it's thought to be better. The reason is simple. Tylenol reduces pain and fever as effectively as aspirin, but is far less likely to cause side effects. That's because it doesn't irritate the stomach lining. So if you've ever taken aspirin, the actual acetylsalicylic acid aspirin, if you take 2 aspirins, it'll upset your stomach if you take it on an empty stomach. If you take too much of it, it can actually cause bleeding in your stomach. So it's a good thing to take sometimes, but you don't want to take too much of it. Tylenol was promoted as being better. You don't have to worry about the risk of aspirin side effects. Unlike aspirin and ibuprofen, Tylenol also, because it's acetaminophen, can damage your liver. And so every year, several hundred people die in the United States because they've taken too much Tylenol. So too much acetaminophen can damage your liver permanently. In other words, if you take 2 or 3 times the recommended dose for a day, you can suffer permanent liver damage. And so over a 10-year span, it's not an enormous number of Americans in the grand scheme of things, but about 1,500 Americans die over a 10-year span from simply taking too much acetaminophen. Taken over several days, as little as 25% above the maximum daily dose, or just 2 additional extra strength pills a day, has been reported to cause liver damage. That's actually kind of small, which until I read about this a few years ago, I had no idea. I mean, all medications usually come with some kind of warning that says don't take more than you're supposed to. But how many of you have taken more pain reliever than would normally be the dose because you have a bigger headache than average? I mean, I've certainly taken 3 ibuprofens instead of 1 or 2 if I'm particularly sore feeling, and not every time. But generally speaking, if you think that 1 Motrin or Tylenol will make you feel better, taking 2 will make you feel twice as good, right? That's usually what taking something that's good for you, we assume, right? If 1 is good, 2 would be better. The problem is, particularly for acetaminophen, it has a very narrow therapeutic window. It's really good if it's taken as directed. If taken as not directed, which is to say as little as 2 extra pills above the maximum daily dosage, it can cause liver damage. Taken all at once, a little less than 4 times the maximum can cause death. A comparable figure does not exist for ibuprofen because so few people have died from overdosing on that drug. It's not really possible to overdose on ibuprofen, but it's fairly easy to accidentally overdose on acetaminophen. So the reason I like this example is that using the wrong concept can have negative consequences. It could have positive consequences too, but in this case, it could have negative consequences. So when I say using the wrong concept, what do I mean here? What's the right concept and what's the wrong concept that I'm referring to with respect to Tylenol? So what's the wrong concept that I'm referring to?
More is better.
Taking more is better because it's a good thing, right? It's a medication, taking more is better. If your concept for medication is, I take a little more if I feel a little sicker, which is not an unreasonable thing to think. If I'm really thirsty, I drink a little bit more. If I'm really tired, I might have more coffee. If I really have a bad headache, I might take more ibuprofen. That's the wrong concept in this case. The right concept is to assume that it's also a dangerous toxin if taken in the wrong way. So probably few of us would look at Tylenol and think potentially lethal. We would think usually helpful. So both of these concepts are accurate. The concept of helpful is accurate. It is a helpful medication. The concept of potentially lethal is also accurate, but it's not usually the first one that comes to mind, though probably it will be from here on in. So using the wrong concept in this case could be dangerous. If you don't know that Tylenol is potentially lethal in higher doses, you might not realize that you're taking too much. And you might say, well, how could I not realize that I'm taking too much? If you look at the ingredients for most cold and flu relief, whatever the brand is, usually acetaminophen is the pain reliever that's in there. So it can be included in lots of other things without you realizing it. So if you're taking a decongestant, multi-symptom flu or cold relief, whatever they are, like Tylenol Cold, for example, but any other brand, Buckley's cold and flu remedy. How many of you have taken these kinds of things when you got a cold? It helps with decongestion, brings down your pain and fever. It contains Tylenol. So if you took those as recommended, and then also thought, well, I also got a bit of an extra headache, I'm going to take 2 extra Tylenol. Now you're sort of in that dangerous zone where you could be damaging your liver without even realizing. So it's important to activate the right concepts to make sure that you know what this medication is represented. Does that seem clear to everybody as a good sort of starting example? So categorization, what I want to talk about is categorization. I'm going to move my window here. The window is actually completely useless in some ways because in other classrooms that I've used, the camera's back there. And so it usually captures me. This is just a document camera that's focused on me only if I'm standing here, which I rarely am. So I understand, I understand the little video of me is actually completely useless. Categorization, we'll define it as organizing the sensory world into meaningful, usable mental structures. So this is a slightly different version of that memory model that I showed you. We had that memory model that had all of the things coming in, all the different versions of memory. This kind of simplifies it. We've got the sensory world. The structure of objects and similarity among objects influence how they are represented in the mind. So everything out there in the world, some things actually naturally go together. You assume that people are part of the category of people because we all kind of look the same. Plants, different kind of plants, you might assume that they're going to be treated the same way because they look the same. You might treat pets the same way because they look the same. So there's a lot of structure in the world that you learn about, but the structure is already there. So that's one important aspect of categorization. We're learning about the structure of the world. A second aspect is that structured representations, which we're going to call concepts, but also can be referred to as schemas or knowledge representations in general, exert an influence on behavior. So the outside world, the sensory world, the world that you live in, has some structure to it. And your job as a learner or as a resident of the world is to understand what that structure is, to represent it in memory so that you can influence your behavior appropriately. So what we'll talk about for most of the class today are these fundamental cognitive mechanisms. How do you bring structure to the outside world? How do you represent things in the outside world? So first, let's start with a couple of basic definitions. And this is stuff that's covered in the textbook. Those of you that were in cognitive psychology with me probably recognize some of these slides as well, because I covered some of that material in one of the lectures. So we'll diverge a little bit as we go, but some of this introductory stuff you'll kind of recognize as being similar. Concepts are mental representation. So when I say you have a concept of Tylenol, or you have a concept for pain relief, or you have a concept for Hubbard squashes, that's a mental representation. That's what's in your mind. When I talk about categories, categories can also be in your mind, but I'm usually referring to the group of things itself. So one easy way to think of that is that concepts are in the mind, categories are the objects themselves, usually out there in the world. So my concept of cat, that's my mental representation. The category of cats are all the cats that I've experienced. And those are the things that are outside. Does that make sense to everyone? Now, I'll often use the same two terms interchangeably when I'm talking about different theories. And sometimes I'll talk about models of categorization, models of concept formation, and so on. But generally speaking, we got what's inside and what's outside. This is something that philosophers have thought a lot about, even before psychologists started thinking about concepts and categories, which is how do humans, and really anybody, anything, how do things bring structure to the world that they inhabit? One philosophical approach suggests that it's nature itself that gives structure to everything that you have in your mind. So the reason you have concepts, the reason you have ideas or knowledge representation is because the world is structured in a particular way. So when Plato suggests that concepts allow you to cut nature at its joints, the implication is that you learn to divide the world up into mental structures according to how the world is actually divided up. If you were to cut an animal, let's say you got a whole chicken and you want to cut the chicken up into pieces to throw on your grill. You wouldn't just sort of hack it randomly. You might pull it apart so that you got chicken wings, chicken thighs, chicken breasts, and chicken drumsticks, right? So you break it apart at the joints. So you're cutting nature at the joints. There's a natural way to cut the world up. And Plato suggests that our job as humans in the world is to learn what that natural way is. any kind of intelligent system, and what do I mean by intelligent system? I mean a system that can learn from its experience. You're an intelligent system. Your cat or your dog is an intelligent system. Computer systems can be intelligent systems, and they can learn to adapt. And it's efficient to categorize things so that you don't need to reinterpret the world each time you experience it. That's kind of what our learning is all about, is not reinterpreting things. When you enter into a classroom, this classroom for the first time, most of you are third and fourth year students, right? You know exactly what to expect. I mean, maybe you don't know exactly what to expect in terms of the content of this course, but you already know how to behave, right? You find a seat that's comfortable, you bring out your laptop, so you already have an idea, a concept of what being in a lecture is like. The first time you were in a lecture as an undergraduate in your first year at Western, you already probably had an idea what that was going to be like, right? Because you had been a secondary school student. So you have a concept, and your concept evolves. High school is different from university, and so your experience was different, but you took what you already knew about being a student in high school, being a student in secondary school, and applied it to being a student in your very first lecture at university. And so maybe you expected slightly different things, but you quickly adapted. So you kind of knew what to expect, and you updated your concept as you went. That's an intelligent system. You take what you know, you take in new information, and you update what you know so that that new information and that new representation can be more helpful each time. Learning would be impossible if you didn't have the ability to do this, if you didn't have the ability to summarize things. So I want to describe a concept or define a concept as a behavioral equivalence class. If there's a question on the midterm exam which says, what's a great definition of a concept? One good definition might be a behavioral equivalence class. This means that an organism treats many different things the same way. So I just behave towards different things. It's a class of objects that I behave the same way toward. I know how I can drink out of any particular coffee mug because they might be all different, but I've treated them the same way. I behave towards them the same way. Does that seem straightforward? All right, good. So let's talk about some functions of concepts. What do we use our concepts to do? This is going to probably seem very familiar to you because it's going to be a lot like what we use memory for. And it's also going to be a lot like the section of the class on similarity where we said, how do we use similarity? And you can see where we're sort of building this model of thinking, where similarity holds things together in our mind. We use our memory to make decisions, and our memory is structured according to similarity, and we call those structures concepts. So we can classify things, we can give them names, we can make predictions, we can reason about things, and we can communicate. So we can assign an object to a category. As soon as we've decided what to name it, we now have access to everything else that we know about it. Once you've identified this decision-making process of classifying an object as an apple, means that you have access to everything else that you know about apples. What are basic facts about apples? You can eat them, right? You can make pies out of them. You can make sauce out of them. They're freshest in the fall, but they can be stored. You can buy them in the store in a bag. You can buy them individually. Lots of different things you know about apples. You probably know individual facts about different kinds of apples. If you're really into apples, the way I am into squash, you would probably know different kinds of apples are better for making apple pie. Different kinds of apples are better for eating plain. Different kinds of apples turn brown more quickly. They get softer. Maybe you like a crispy apple. Maybe you like a soft, sweet apple. I don't know. There's preferences of apples, but you probably have one, and you have a concept for them. We can name all kinds of objects. Quick scan here. Either scan this on your phone or do it on your device if you have your device, and just quickly name some objects. So you're going to see a series of pictures. Each picture just asks you to give a name for it. And just put the first name that comes to mind, or the name that seems the most appropriate for the object. And then we'll look at what you've done. It doesn't hurt to start with a cute dog or a cat or something like that. I don't know about you. Look, some of you that have been in my class before, I don't know if we did this in cognitive psychology, but I would do this every week, usually about this time through the course in psychology of thinking last year, is that this time of year, late January, early February, how many of you would say this is your favorite time of the year? Nobody says this is their favorite time of the year because it's an awful time of the year. The weather is awful. This is about the time that things start getting tired. And I don't know about you, but I am really I'm feeling down about the world because of, I won't go into all the details, but I'm sure you probably can imagine. There is unhappiness and unrest, misery, death, and destruction in many parts of the world simultaneously. And if you're a person with any reasonable amount of empathy, you probably start to think about these things. And it's not always helpful, even though it's important to think about these things. So it's a bad time of the year. The weather is terrible. There's bad things happening everywhere. It's really hard to not have some of those things rise to the forefront. Starting with a picture of a dog can at least help to look at something a little bit happier. One of the things we used to do in class was we would start, I should have done that today, we would start with, what are some pieces of good news? Does anybody have, well, I'm sort of waiting to draw this up. Does anybody have something positive, just a short piece of good news, like I got a new plant that you would like to share? Anybody have any exciting good news stories? It's a whole 3-hour class on concepts and categories. It's going to get kind of dull. So if we can, does anybody have a piece of good news? Has anybody acquired a new thing that they're excited about? Yes, thank you.
Pandas got off the list.
Pandas got off the endangered species list. I did not know that. Congratulations, pandas, for not being on the endangered species list. Good job, pandas. I'm so proud of you. Any other comparable? That's a great piece of good news. So I'm happy for them.
Pair of shoes.
You got a new pair of shoes. That is good news. Congratulations on the new pair of shoes. I hope that the new pair of shoes didn't inadvertently, in some butterfly effect, kick the pandas off the endangered species list. I can't see how that could possibly happen, but you never know. One little thing. But I'm really happy about your new shoes. Anybody else have a comparable piece of good news? New shoes, pandas, etc. You're getting your hair done today. Good for you. That's really good news. Yes.
My roommate made me a really nice dinner last night.
A nice dinner made by your roommate. That's very lucky. So congratulations to you and your roommate on the nice dinner. I promise I'll start every class like this. I actually meant to do this today because I looked outside and I didn't even want to be here because of the weather. So I think it's good to start with a little bit of good news. There's a lot of bad news in the world, and new shoes, haircuts, good dinners, and pandas are all examples of good news in my opinion. Okay, while we're on the positive vibes here, we've also got a dog to look at. Let's view our responses. More details. Well, that was pretty unanimous. Somebody gave it a Labrador, but everybody else said dog. Somebody said golden retriever, Labrador retriever, lab dog, puppy. So almost everybody says dog. So kind of almost unanimous. And you'll notice that the ones that were not unanimous were a subordinate level. They were a more specific level. Anybody who named this as a lab, did you name it as a lab because you have a lab? Or because you just really like labs, or you just want to be precise? You have a lab. So you named it as a lab because you're like, that's a dog, that's a lab, a Labrador retriever. So that's one example of how we conceptualize things. Most of us just say dog, but some of us might be a little bit more specific. Nobody said animal, though would also be a correct answer. Everybody says dog. The next one was a picture. Let's go to object naming here. Next one is a Stanley Dynagrip hammer. Everybody is pretty unanimous there. Somebody very specifically said Stanley Hammer. Good job. Somebody said tool. That's really nice because that's an example of where most people don't choose to name the object at what we would call, what we're going to call later, the superordinate level, the level above. So hammers are tools. They're members of the tool category, but most of us, when we see it, we name it as a tool. Even though we could easily say, or sorry, we name it as a hammer, we could easily say a tool, and somebody gave it a more specific example, which is a Stanley hammer. So almost all of us say hammer, but there's some deviation, and the deviation is predictable. We don't need to look at all of these, but let's look at a few more. Here is a car of some sort, which most people say car. Somebody said a Hyundai. Somebody was very specific. Blue car, less specific. So again, a little bit of Hyundai. Somebody's got the subordinate level there because probably, I'm assuming, either has that car or has had that car. We've got Apple. We've got cat. Not much specific. Somebody says meow. Maybe they're really into that particular cat. But for the most part, we don't get too specific with cats. Even if you like cats, you're not going to get too specific. Nobody says animal. And probably, I don't even know what kind of cat breed it was, but I don't know. I mean, I love cats, but like they're all kind of similar. So I would just say cat, even if I guess it's a tabby cat. So the point that I want to make with this is that we kind of name things in a predictable way. Later, we're going to talk about these examples in a little bit more detail. We're going to talk about why we all named things, almost all of us named things the same way. Most of us, when seeing the Hyundai car, said car. A few said Hyundai. A few said blue car. Most of us, when we saw the Stanley hammer, called it a hammer. One person said tool. One person said Stanley hammer. So we kind of choose a predictable way to name objects. We're going to refer to this as the basic level. Basic, not because it is base, but because it's kind of the first thing that comes to mind. It's really the basic level that you start at. When you interact with the world, there's a predictable way in which you conceptualize it. People are a generic category. Dogs are a generic basic level category. Fruit is a basic generic level category. And so the names that you apply to this basic level tend to be the first ones that come to mind. They're short. You learn them earlier when you're younger. They're the first things that you name. But one of the things we'll talk about in a little bit too is that if you're really familiar with a concept, if you're really into Hyundais, you might be very specific to name it at that level. In other words, if you're kind of an expert in something, then you tend to name the object at that subordinate level. We make predictions, we make inferences. We gave the example in the similarity lecture about the Hubbard squash. We might say, well, I've now seen a lot of Hubbard squashes, so I kind of know exactly what's going to be in there. I don't know every squash. Someday there might be a squash I open up that's a different color on the inside. But for the most part, I'm pretty comfortable in my prediction because it's in a category that I know. If I know some things about the category, I probably can predict other things that I can't see. That's what inference is. It's when you know some things about a concept or a category and you use your knowledge about that concept to predict the things that you don't know, to predict the things that you don't see. You can react to objects, you can behave towards people. Reasoning, categorical knowledge is used to solve problems. So in a few lectures after the midterm, we're going to talk about deductive logic, and we'll talk about deductive reasoning about a group. Categorical reasoning, categorical knowledge, knowing that all members of a category have some property, and then using that to think about other objects that might be members of that category.
Is inference synonymous with induction?
Inference in this case is synonymous with induction. So when we talk about inductive reasoning, it's a good question. Inductive reasoning means that you're making inferences based on categorical knowledge. Representativeness, this heuristic that we talked about, is an offshoot of our tendency to think about things, reasoning about an individual as if they were representative of the entire class. You see this often when you're interacting with people. So if you're interested, how many of you are interested in social psychology or understanding about how people react to groups, making stereotype decisions? Those are all examples of reasonings based on categories. What's the first thing that comes to mind in this picture? What are some names, some ideas, some concepts, some inferences, and some predictions you might make? He's a cop, right?
Big.
Pig, okay. Well, I mean, he's kind of a friendly police. I'll give you, everybody has their own experience with the police. I would generally assume that this is in the friendlier vibe because he's smiling. Yes. Donuts? Okay, so we've got stereotypes about law enforcement. We have stereotypes about cops and police officers. Other things that might come to mind. You might be expecting a ticket or a citation. Perhaps you have parked in a place where you're not supposed to park. Perhaps you have engaged in an activity such as carrying around an open container when you're not supposed to. And he's coming to approach you. One of the things that I wouldn't activate is necessarily a high fear response, though. This isn't a particularly fearful looking police officer. Generally speaking, you could even imagine that what if you were in a situation where you needed some assistance? There was somebody who made you feel uncomfortable, let's say, or your car broke down, or you were having, you needed some emergency assistance, and you approached this cop. You might actually activate sort of a helping framework or a helping concept. He looks like he's there to help. He might be giving you a ticket, but he also could potentially be there to help. How about these police officers? What comes to mind in this case? What are some concepts that come to mind?
Scary.
They're a little scarier looking. Why are these police officers a little scarier looking?
They're holding weapons.
They're holding weapons. I mean, that's a really big one. We assume down here out of the view that he might be have a holster with a service revolver. That's likely what he has, a 9mm or something like that. That would be his regular issued weapon. Not surprising. Probably has all the other things that police officers have. But these guys have much bigger weapons, and they're holding them out front, and they have other stuff. What are some other concepts that might come to mind?
Dangerous.
This is a dangerous vibe. Whereas, depending on your individual relationship with law enforcement, if, for example, you are driving your Hyundai really fast and you're used to somebody coming up to you with this look on your face, maybe you're sort of expecting to pay something. But it's not an unfriendly vibe. He's not giving off a menace. These guys could also be thought to be helping you. If you were in a situation where perhaps maybe there was a riot going on and they're there to protect businesses. If you're a business owner and there's a lot of unrest and they're back making sure that businesses aren't being threatened, they could be helpful, but it is definitely signaling to everyone that there's something more dangerous going on. They don't, their faces are partially obscured with sunglasses. They've got body armor on. They've got large weapons in front of them. So there's definitely a more menacing vibe, even if they're there to protect you in some way. They're protecting you from something that's a little bit more dangerous. There's in between. Most of the London police who you might see at any given HOCO or FOCO event aren't particularly menacing. They're usually there to make sure that the road doesn't get too crowded and to make sure that if there's trouble, an ambulance can arrive, or to make sure that the crowds don't get too out of control. And you know what they do. How many of you've all probably, if you haven't been to HOCO or FOCO celebrations, you certainly know what the routine is, right? There's a lot of activity on one street. The police close that street. The activity moves to the next street. The police close that street. The activity moves back. And mostly they're there to sort of keep things from getting out of control. They're not there to stop the party from happening. They're there to keep the party from getting too dangerous for anyone. And so it's not really a menacing vibe. They're not carrying around semi-automatic weapons. They're wearing things that can be easily identified as police. So we have different concepts. And as we all revealed, your concepts might reflect your own particular relationship. If your relationship with law enforcement has generally been positive, if you expect them to be helpful, if you have very little experience On the other side, being if you've never been arrested, then you might not expect to be. On the other hand, if your personal experience is one in which you've been on that sort of other side, you've been arrested before, or you've been targeted before, or you've been in situations where there's a lot of unrest, you might develop a more negative stereotype of law enforcement. So a lot of it is held together by the features. These features are ones that activate a more dangerous scenario than these features. But there's also some aspect of your own personal experience. So that's another example about categories being used for prediction. It's what your knowledge is. Also, that knowledge is activated by the features that you perceive. This concept might be different from this concept, and it's intended to be that way. And this concept might be different. And again, it's intended to be that way. Those features activate certain concepts and certain schemas for most of us. Does that all seem pretty straightforward? Okay, so we're going to talk about different theories of concepts. I'm going to talk about some introductory stuff with what's known as a classical view, and then we'll take a short break, and we'll come back and talk about some alternatives to the classical view. Some of the key questions to keep in mind, and I talk about this in the textbook as well. Key questions are when you form a concept, when you form a mental representation that we're going to describe as a concept, you're always leaving some information out. Remember a few slides ago, I said that an organism learns to form a concept in order to be efficient so that they don't have to re-experience information as if it's new each time. That means that you're going to probably lose some information. Maybe you're not going to pay attention to certain features because you already have an idea of what to expect. If you lose some information, you abstract other information. So different theories of concepts and conceptual representation emphasize how much information is retained and how much information is lost in the abstraction process. If that doesn't seem clear now, it'll seem clear as we go on when we talk about some of these different theories. But the representation is assumed in a behavioral equivalence class to try to minimize the individual variation among objects so that you can maximize how they are alike. That's what your behavioral equivalence class and your concept is. It's a way to represent a lot of different things and to emphasize how they are the same. If you emphasize how a lot of things are the same, you will de-emphasize how they are different. So your concept is usually something that abstracts what's the same and ignores what's different. And so the different theories differ in terms of how much information is retained and abstracted and how much information is lost. We also want to consider what cognitive mechanisms play a role, and we're going to talk about some hierarchical models, some classical models, and some probabilistic views. These models are interchangeable. Just like when we talked about similarity, I suggested there is no one right theory. There's not one theory that captures everything. These are different theories that have been developed over the course of different decades that emphasize different ways in which we store information. Some of these emphasize the relationships of objects within and between categories. That's what this hierarchical model represents. And other theories represent the nature of the representation itself, whether you're paying attention to features, rules, or memory traces. So let's talk about some of these key questions in the hierarchical view, and then we'll take a quick break. So we started with some naming examples. You named some objects, and I suggested that we would name them at different levels. We might call these fruits, we might call them apples, or you might name Honeycrisp, Granny Smith, and whatever these other ones are. So there are at least 3 different ways to categorize or name any one of those objects. But most of us chose apple. There are lots of different ways to name these objects. But most of us would call them hammers rather than tools or Stanley hammers. So why is that? And what's the relationship of one level to the other? So this is captured by an idea of concept formation known as hierarchical representation. The idea of a hierarchical representation is that when you have a concept, when you store a mental representation, When you form a concept of an object, you don't need to form or store everything about that object with that concept. Let me go back to the previous slide and talk about that, and then we'll go forward again. But on this previous slide, we've got apples here. So apples are fruits. Fruits have some properties that are true about all fruits. They have seeds in them, right? They're the part of the plant that has seeds. So if you know that about fruits, you don't need to know that fact separately and independently about apples. What you need to know is that apples are fruits. Once you know that apples are fruits, you know that they have all of the properties of fruits as well. If they are plant matter, you know all of the properties that might be true of plant matter are going to be true of everything that's below that. So you don't need to store everything about fruit that you know with your memory for apple. You just need to store what's particularly true about the apple concept. Does that seem to make sense? So it's a way to organize the world so that you don't have to store every particular fact that you know about an object with every object that you're familiar with. So there's different levels, and how do we know which one to use? And by use, I mean, how do we know which one to access and reason from? So if I talk about using a concept, I'm usually talking about using it to make a decision, using it to solve a problem, or using it to make it. So here's one way that you can imagine representing a lot of different things. This is the one that's in the, this is the figure that's in the textbook. And this comes from an early model of conceptual representation, first devised by two psychologists and cognitive scientists named Collins and Quillian. Collins and Quillian were interested in knowledge representation in general, and whether this was knowledge representation in a human memory system or a machine memory system, suggested that a hierarchy is a really efficient way to represent a lot of information. And here's how it works. The idea is that when you think about a particular bird, a canary, let's say, canaries have some properties that not necessarily unique to canaries, but very characteristic. Canaries sing and they're yellow. Does anybody have a pet canary? People don't have pet canaries these days. I don't know anybody who has a pet canary. I'm not sure I've ever even seen a canary except once when somebody's pet must have gotten loose and there was this bright yellow bird in our backyard. And we're like, what the heck? This makes no sense. Why is there this bright yellow bird? And I said, it's a canary. What is even a canary? Why is it flying around? It must have been somebody's pet, but people don't normally have pet canaries, but you probably have a concept of what a canary is, right? It's a yellow type bird. It's a pet bird, and it can sing. Maybe there's no other fact you know about canaries. But you also know that canaries are birds. And so if by knowing that canaries sing, are yellow, and are birds, you have three pieces of information that you might store with your representation for canary. They sing, they're yellow, and they're birds. But by knowing that they're birds, you have access to all of the information you know about all birds, which is they have wings, they fly, and they have feathers. I understand that some birds do not fly, and that's an exception case, which we store separately. But generally speaking, birds have those properties. So you don't need to know all of that when you think about a canary. You just know about canaries being birds. You don't need to know that canaries are birds and that birds are animals. Animals might have skin, they move around, they eat, they breathe, and so on. So there's lots of things that are true of animals, which are definitionally going to be true about birds and canaries as well. But most of us don't store that information in our memories the same way. You probably don't have a knowledge representation or a concept for canary that includes the facts that canaries have skin, that canaries can breathe. It's just not a piece of information we just store. Does that make sense to everybody? So that's what a hierarchical representation is. It's a way to assume that at different levels, there are different pieces of information that are most relevant for that idea. For animals, yes, it's important to know that animals are things that eat, breathe, move around, and have skin. For canary, we need to know that they sing and they are yellow and that they are birds. These different levels, in addition to sort of being efficient, also seem to have some properties which define why they are. So if the question is, why do people use, why do we use a certain level? Why are there certain levels? One possibility is that the structure of these levels exists in the natural world, which means that it exists in the way that you perceive the natural world. Here's another representation, again, including animals at a superordinate level, sort of at the top. Super just means top in this case. A subordinate level, which is sort of at the bottom, most specific, and a basic level, which is kind of in between. Most of us would have more than 3 levels for any particular knowledge system. I'm using 3 just to sort of make it straightforward, but you can certainly imagine being more specific, eventually going down to an individual poodle. If you have a poodle as a pet, that would be one pet. That would be my pet. That's a category of 1. And it could even be more specific, I suppose, because you could have my pet today. That's one very specific subordinate category. It's a dog, it's my poodle, and it's my poodle today. That's a representation. So these are different levels. And one of the things that I want to point out is that these different levels, the concepts or the ideas have relationships with themselves within a category and also between categories. At the highest level, at the most abstract levels, concepts don't really resemble each other very much. So the concept, the high-level concept of animal, doesn't resemble the high-level concept of plant or vehicle very much. And you can imagine lots of other concepts up there besides just those 3. And it's clear that they don't share a lot of resemblance. Animals aren't like vehicles. And vehicles aren't like plants. And plants aren't like games. There are lots of high-level categories, and the similarity between the concepts isn't very high. The similarity within the concept isn't very high. And by that, I mean, if animal is a concept at this high level, it has a lot of variability. There are a lot of different kinds of animals. We're animals, sponges are animals. I guess worms are animals. I mean, there's all sorts of animals that differ. So there's a lot of variability. In other words, there's not much similarity within categories either. Similarity isn't a very important aspect of high-level abstraction. Does that make sense to everybody? At the lowest level, similarity tends to be fairly high within categories and between categories because poodles have a high level of similarity with other poodles. Because they are a subordinate category. They have similar shapes, similar behaviors, similar characteristics. Poodles also have a high level of similarity with other subordinate level categories of the same type. So poodles might be highly similar to Labrador retrievers and German shepherds too. Not exactly, but enough that you would say, well, they are kind of the same shape. They are kind of the same. They have a lot of the same behaviors. They have many characteristics that hold them together. So similarity isn't very relevant at these high levels, and it's very relevant at low levels, both within a concept and between different kinds of concepts that have different names. At this in-between level, which we've referred to as the basic level, at the basic level, similarity is high within a category. Dogs are like other dogs, but dogs are enough unlike other cats and lizards and cows that you can reliably tell one from the other. We don't tend to make mistakes identifying cats from dogs. We might make mistakes identifying different dog breeds or different cat breeds. So at this basic level, one of the reasons we tend to operate and identify objects at the basic level is that the observable similarity, featural similarity, is pretty high within a concept so that we can activate that concept and come up with a name. But it's low enough between different concepts that we can reliably use similarity as a way to identify the object. So that's one of the reasons why most of us name things at this basic level. Let's talk a little bit more about basic level categories and then take a short break. Does that seem okay? Does everybody have 10 more minutes left in them? I know it is not the kind of day that you wanted to be here. I completely understand because I myself did not want to be here on this day. I don't know how far you had to drive or walk or take the bus, but it was longer than I wanted it to be. Let's just put it that way. But we're here. So let's try to go 10 more minutes, take a nice break. So basic level categories. high level within category similarity, members of a category tend to be similar. A low level of between category similarity, members of contrasting categories tend to be dissimilar. That means that for completely objective and observable reasons, this would be a great level at which to name objects and at which to interact with objects and make predictions from. So I'm going to talk a little bit about some basic level category research. This is from the textbook. In a series of highly influential studies, Eleanor Rosch and her colleagues developed a number of operational definitions of the basic level. First, the basic level of object categories was shown to be the most inclusive level at which category members possess a significant number of common features. So in other words, it's the most abstract level, it's the highest, most abstract level at which things tend to still be similar to each other. The most inclusive level at which most members possess a similar or significant number of common attributes or features. In a second study, Rosch found that basic level categories are the most inclusive for which highly similar sequences of movements exist for category members. Dogs move the same way as other dogs. Cats move differently, even if you don't have a name for them. Even if you haven't yet learned the name of cats and dogs, even if you have limited experience, you can know that cats move differently than dogs. So you can tell that they're different things. Different species of dogs might look different. Labs and poodles and German shepherds and Newfoundlands look different, but they kind of move the same way. Cats move differently. Dogs move differently from cats. Cows move differently, and so on. So that's another way in which this category definition works. Objects within basic and subordinate level categories have shapes that are more similar than objects within superordinate categories. So in other words, shape similarity at the basic level is highly similar. And there's lots of different studies that have shown. So I don't expect you to know each one of these studies. I would expect you to know the general idea that when people list features, they list features at the basic level. That basic level categories share the same movements. That shapes are common. That basic level categories are more effective as primes for visual comparison. That people label and categorize them at this basic level. They're overwhelmingly preferred in free naming. That's sort of the study that we did at the experimental demonstration we did at the beginning of class. I asked you to just name them freely, didn't give you any constraints, and all of us overwhelmingly preferred the basic level name. The structures, they're often mass nouns. Subordinate names often include basic level names, like domestic short-haired cat includes the basic level name in it. Subordinate names in ASL are composed of signs for basic level names. They're more frequently used in talking to children. They're more frequently used in text. So there are a lot of characteristics of basic level categories that are both functional, structural, in terms of how the world is formed, and behavioral, in terms of how we name them and interact with them. Another way to think of it, basic level categories are informative and distinctive. Superordinate, not very informative, but very distinctive. Subordinate, informative, not very distinctive. Atypical subordinates, these would be things like ostriches, which are atypical for other birds. Atypical subordinates tend to be informative and distinct. Most of us have lots of exception categories. We'll call these atypical members. Does this all seem straightforward? Okay, good. Let's do another category naming task, and then we'll look at the results, and then we will take a break after we look at the results. These are not super interesting demonstrations, but they're just interactive enough to keep everybody from completely zoning out on this particularly cold day. It's not as cold in here as it was last time. Take a few more minutes on this. We'll look at our results, and then we will take a short break. Or actually, let's just take a short break after you're done here. So you can just take your time on this, rather than coming back, looking at the results, then taking a break. Why don't you just take your time on this? I'll just leave this open and let's take a break for 10 minutes or 15 minutes as normal, and come back and look at the results. That way we'll make sure everybody has had a chance to complete this.
Right.
I'm just trying to read the room here, and I feel like it's early break time is better than slightly later break time. Oh, I'm going to pause the recording here.
We need a nap break.
Okay, hi everyone. More or less, it seems like we're kind of, everybody's back. The density of people in the room seems like it was roughly like it was before the break, so I'm assuming everyone's back. Let's take a look at the answers if you haven't already finished. Then we're going to talk a little bit more about hierarchical models, and then we'll talk about some alternatives. I think we're still on track for this slightly before noon finishing time. So I asked you to name, let me hide this. Okay, so I asked you to name some categories. We started with fruits, and we're going to go with what. Let's look at our answers here. Well, actually, first, let me look at our big picture here. And it appears as if the word cloud, I don't know how to set the density of word clouds on Microsoft Forms. I have no idea how to set it, but it appears as if most people said apple. A lot of bananas and a lot of strawberries. Obviously, there are going to be some others, but those seem to be the most common. Let's look specifically at what some of these answers are. Go to more details. Okay, so tomato, apple, cucumber, oranges, apple, pear, banana, orange, mango, strawberry, apple, banana, orange, apple, banana, strawberry, apple, apple, banana, apple, orange, mango, apple, apple, pear. This is a nice one. Persimmons, kiwis, banana, apple, mellow. That's a nice list there. Way to flex. Apple, banana, banana, strawberry, dragon fruit, apple, apple, plum, grapes, apples, apple, strawberries, apple, banana. There is an awful lot of apple, banana, a lot of apple, orange. So there's some commonality here. So the point that I want to make is that we tend to list things in particular orders. So not only is fruit a basic level category, but we tend to respond to fruit and list attributes or list members in a fairly predictable way. There isn't one answer to this question that's right. There is no one typical fruit. But if we were to look at the things that most of you listed first, apple, banana, and strawberry kind of come up towards the top. Now that's actually kind of interesting to me for a couple of reasons. First off, why would apple be first? What's kind of unique about apple?
What apples a lot today?
Had a lot of apples. We've talked about them a lot today. We've given a lot of examples of apples. What's another good reason why apple would be the first or most commonly listed?
Right, and
It's a highly consumed fruit. We're just familiar with it. It kind of sits in the middle of the fruit category for a lot of us. If it isn't the middle, it's definitely one of the most typical because it's familiar to us, it's common. It has attributes that we think of that are really common to fruit. What are some of the features of fruit? If I ask you to list what are features or rules or characteristics or attributes that are common to fruits, what are the things that come to mind? So not fruit examples, but fruit features. What defines a fruit?
They usually form from the flower of a plant or tree.
They form from a flower. Apples do indeed form them from the flower of the apple tree.
Seeds on it.
They got seeds on the inside. Apples got seeds on the inside, even tiny little seeds that aren't very useful. You can't really plant them for anything, but they're there.
Like colorful.
They're colorful. Fruits are usually colorful. So apples do indeed fit that category. What are some other things about fruits?
Usually sweet.
They're sweet. They're usually sweet. They usually, by sweet, that also implies that you eat them. So they're noticeably sweet.
It's healthy.
Usually healthy. It's a healthy thing. We tend to think of fruits as kind of a healthy thing. So an apple a day keeps the doctor away, so they say. I don't know what that really means, but I guess that just means eat lots of fruits and you will be less sick. So we could probably agree that although strawberries have this characteristic, they clearly are fruits, even though the seeds are kind of on the outside. Bananas are interesting because they're a lot different from most other fruits that we would have listed. Is there a seed in a banana? Is that little thing at the end, is that really the seed, or is that just like some less? I don't even know, actually. I should know. But bananas seem a little unusual in terms of how they are categorized as fruits, but they're familiar to us. So they're functionally really good fruits, even though they might look different from a lot of other fruits in the sense that they're shaped different. A lot of fruits are round, aren't they? There are no seeds on the inside of a banana. The banana is mostly non-fruit. Can anybody verify that the banana has a seed at the end? I've always thought that little brown thing at the end was the seed, but I actually don't know if that's true. Yeah.
That they used to.
We'll never know
It
this.
used to. That's a vestigial seed?
Yeah, we.
Okay.
Out.
So it's no longer it's no longer a plantable seed, which is true for apples too. It's not really a plantable seed, but it's kind of a vestigial seed. Okay, so bananas kind of do fit that category. At least the bananas that we eat are not really very fruit-like. They're not really bearing any seeds. They can't be replanted, but they're consumed in the way that fruits are. So we can see that bananas are there for a reason. But a lot of these other things, let's go back to this more details again. Let's go down towards the bottom here. We didn't get everything. Pears fit this, watermelons fit this, cucumbers fit this. And some of us listed things which are sort of in the maybe less sweet fruit category, like tomatoes and squash and pumpkins and cucumbers, but they still fit that general definition. They got skin on the outside and seeds on the inside, and they grow from a flower. So we kind of know what it means to be a fruit. We know how fruits are used, and apples really seem to fit a lot of that. Bananas fit a lot of that for us, in terms of at least the eating part. Oranges seem to fit a lot. Strawberries seem to fit. So we have an idea of what fruits are, and apples, bananas, strawberries, oranges, etc. They all kind of fit what a lot of that concept is. Start this over again. I've been prof for like 20 years and still don't know how to use PowerPoint in a way that makes it look like I know what I'm doing. Okay, now it looks like I know what I'm doing. So basic level categories. We said there are some characteristics. Let's just wrap up our discussion of basic level categories. We're going to name them faster. Children list them first. They have short names. They tend to be listed first. If you're asking people to list plants, you're going to list common things like fruits or trees rather than very specific things. Most people are experts at a basic level, meaning that that's what you're familiar with. To describe an expert as someone who is experienced doing something, you are experienced with naming things at this basic level. And here's where we can deviate just a little bit, forecast some of the stuff we're going to talk about when we discuss expertise. And that is that experts tend to name things at the subordinate level. We saw that a little bit when you named pictures. One of you happens to be an expert in hammers, maybe. One of you has a lab, so named it as a lab. One of you happens to be an expert in Hyundais, and so named it as a very specific Hyundai sports car. So some of us might be experts in a particular domain. You might be experts with fruits or apples or bananas or cars or anything. And so maybe if you're an expert, spend a lot of time thinking about things at the subordinate level. And so that high level of between category similarity starts to seem less high because you're really familiar with the things that are specific to those subordinate levels. This can be seen in things like expert bird watchers. And later we're going to talk about tree expertise when we talk about experts in a future lecture. How many of you would consider yourselves to be at least modestly interested in bird watching? In the sense that you like birds. I don't see who wouldn't like birds. But if you ever have thought about identifying particular species of bird, now I don't mean to the level where you would spend your entire year trying to classify as many particular kind of species as possible, but if you give a shit about birds, maybe you're a bit of a bird fan, okay? So you can tell the difference between an eagle and a robin. That's at least a reasonable amount of familiarity. So those are subordinate level categories, and you'd be able to tell them. But if you're really into birds, you would probably naturally, instinctively behave at the subordinate level the way most everyone else would at the basic level. Expert's basic level is subordinate for everyone else. Here's a study. So we've been talking a lot about facts. I've been giving you a lot of basic facts. We haven't talked about any experiments yet. Let's talk about an experiment that James Tanaka ran a number of years ago. It's quite a number of years ago, looking at expertise in basic level categories. Object categories and expertise is the basic level in the eye of the beholder. Yes, the basic level is in the eye of the beholder. The more expert level knowledge you have, the more specific your basic level is. Here's how they ran this experiment. Subjects were dog experts recruited from a local dog organization and bird experts who were members of the local bird watching association. So you got a club of people, a kennel club or a dog club. These are people who are really into dogs. And when they think about dogs, they don't just think about their own dog, they think about a lot of dogs. So if you're a real big dog person, that would be you. If you were a member of the local bird watching organization and you were really into birds, this might be you, a bird expert. And so what they did essentially was this. We've got key thing here is that none of the subjects had expertise in both dog and bird domains. In other words, dog experts pretty much didn't care about birds at all. And the bird experts didn't really know much more about dogs than the average person. So you've got a bunch of people who are really into dogs, but really don't care much about birds, and a bunch of people who are really into birds, don't care so much about dogs. So you're experts in only one thing. Then we're going to show them black and white drawings and photographs of common objects. This is not unlike what we did at the beginning of this class, just photographs or drawings of things, and you're naming them. The artifactual categories, artifactual just means non-living things, things that are human-made, artifacts, of tools. Artifactual and natural kind categories. Artifactual categories were musical instruments, sports equipment, vehicle, food, furniture, tools, clothing, footgear, jewelry, office equipment, cooking utensils, kitchen appliances, home electronics. And mixed in there were a bunch of natural things like dogs, fish, birds, insects, trees, flowers, vegetables, fruits, four-legged animals, famous persons. So here's a lot of different objects. And for almost everybody in this experiment, they should be naming them at the basic level because they're not particular experts in anything. We assume that the average bird watcher is kind of general level knowledge for footgear, unless there's a very specific kind of footgear that's good for watching birds, which I don't think there is. So they're pretty much the same into shoes as everyone else. Same thing with jewelry, office equipment, etc. But there are also some birds, robins, sparrows, jays, and cardinals. And there are very specific kinds of dog, German shepherds, Doberman pinschers, beagles, and cocker spaniels. And so what we have is a bunch of different objects, and embedded within that, a group of pictures that happens to be the thing that you are most into, whether that's birds or dogs. Subject was seated at a table directly across from the experimenter. Subjects were instructed that they would see a series of pictures depicting common everyday objects. Their task was to say the word that names the object as quickly as possible. This is a lot like the task that we did in class just about an hour ago, except that you're saying it instead of typing. The experimenter presented each picture one at a time and reported the category level, superordinate, basic, or subordinate for each response. The target pictures the domain expertise, noted the order of appearance, etc. So basically, you're sitting there, experimenter's holding up a picture, and you're just saying the first thing that comes to mind: hammer, necklace, robin, that kind of. And what's important here is that dog experts use subordinate terms for the dogs, but not for the birds. In other words, if you are a dog expert, so experts are people who are shown in black. And the dog experts here, your dog experts, when they're naming dogs, they use subordinate terms. When they're naming basic categories, there's no difference. So they name the, dog experts tend to choose dog names more often than bird experts. So they're novices in birds, experts in dogs, and that's what that gap is supposed to show. When they're naming birds, on the other hand, they tend to do so at the basic level. And bird experts are different, even more extreme. Bird experts, because being a bird watcher is all about identifying bird species. Being into dogs is a little bit less. Being into birds means that when you see a species of a bird, the first thing that comes to mind is the subordinate level. You're much less likely to name birds at the basic level. You do that for dog. And so what it's suggesting is that experts walk around like everyone else, naming things at the basic level, interacting with the world at this basic level, except for the thing that they're experts in. For the things that they're experts in, they're really good at coming up with those sub and subordinate levels. That's means that they are operating at a basic level that's more specific than an novice is. And that has to do with their level of experience, the number of years that they've spent operating at that level. Does that seem straightforward to everyone? So a key aspect of basic level categories is that most of us interact with the world at the basic level, but for experts, they operate at a more fine-grained level of analysis, at a subordinate level. Okay, so keep in mind some of these ideas of hierarchical organization. One of the things we didn't talk much about at the hierarchical model is exactly what is being represented at each unit, at each hierarchy. Is it a cluster of memories? Is it a list of features? We've kind of implied that it's a list of features. Is it a set of definitions? Maybe. Or is it a single prototype, a single best example, a single abstraction? So what I want to talk about for the rest of the class are models of categorization, models of concept formation that get at that question. Not the relationship of one concept to the other, but what one concept actually looks like. Is it a bunch of memories? Is it a list of features or definitions? Or is it an abstraction of something? And we're going to call these either a classical view, any model that assumes that you store a definition or that you represent a concept by a set of necessary and sufficient conditions, like a set of rules. That's usually referred to as a classical view. Categories are defined as strict classes. And some concepts are formed that way. Most other concepts are probabilistic in nature. So when I say a concept is probabilistic or category membership is probabilistic, I mean that there is, for most concepts, there are multiple categories you could put an object into. Everything belongs to more than one category. And sometimes objects can belong to very similar kinds of categories, depending on how much you know about them, or depending on the kinds of features that you pay attention to, and that relationship is probabilistic. So apples are really good fruits. They're like 100% fruit. Maybe tomatoes are 70% fruits. You kind of know that they're fruits, but maybe there's some ambiguity. And maybe there might be things like pumpkins or Hubbard squashes, which are fruits technically, but are less likely to be classified as fruits by most people. So they're probabilistically less good examples. That's what I mean by probabilistic category membership. Is that okay so far? All right, so let's talk about the classical view. Classical view is one that's kind of strict in its definition. Classical view assumes that your concept or your category So a category of things is represented in your mind, and a concept is a set of necessary and sufficient conditions. In other words, all of the things, all of the properties of an object that are necessary to be categorized, and that set of things is sufficient to be categorized. If a category is defined by a set of necessary and sufficient conditions, it also implies that category membership is very binary. Things are either members of a concept or a category, or they are not members of a concept. Because if the set of features is necessary and sufficient, as long as you have those features, as long as the object possesses those attributes, that's all that's necessary. If you possess more features, then you're possessing more than what's necessary. That shouldn't influence your decision. In other words, as long as an animal has dog DNA, it's a dog. There's no good dogs and there's no bad dogs. So I think they're just good dog. Anything that fits into that category is a dog. So a lot of concepts for us are kind of like that. Even if we can think of exceptions, and even if we can think of cases where the definitions are hard to come up with, there are still lots of concepts for us for which we usually approach them as if they are classically defined. We talked about one a few weeks ago when we talked about the 3-inch round object and the highly variable pizza category and the non-variable quarter category. And I suggested that the quarter is a classically defined category. Things are either quarters or not. They have to possess those set of necessary and sufficient features, which has to be made by the government in order to be a quarter. Otherwise, it's a fake quarter, right? You can't just make your own quarter. Quarter has an essence, and that essence is necessary for category membership. So that's an example of a classically defined category. Kin relationships are sometimes classically defined categories. There are only so many ways you can define your sibling, or sister, or your brother, or a parent. That can be a parent, a step parent, but your parent is a biological entity. So if you are the offspring of someone, they are your parent. If you are adopted by someone, they are your adopted parents. There are strict definitions for what these kin relationships are. We had a discussion in my family a little while ago because my father posted a picture of a baby and said, great-grandchild number 4. And my daughter said, whose baby is this? Because I would have known if one of my brother's kids were expecting a child. I feel like I should have known this information. And we're like, who had a baby in the family? We didn't know about it. And it turned out it was a step-great-grandchild, which I didn't know was a thing, but is a thing. And I wasn't really paying attention to my brother's wife's daughter from his wife's first marriage. Son. Who is this? We had to actually ask ChatGPT to figure out what the relationship was for me to this child, but my dad knew that it was a step-great-grandchild. So it's a classically defined category. There is one definition for step-great-grandchild. I didn't know it was a thing, but it is. And that is exactly what it is. It's the offspring of a stepdaughter or stepchild. And that's what this baby, whose name I don't remember now, is. Because there's a lot of distance between one's step. What is that child to me now? I've forgotten, but I looked it up on, this is a good use for AI. So that's a classically defined category. Even if I'm really close to this person, there's only one definition for what that relationship is. An easy one is mathematical and geometric categories. A square is an object with 4 equal sides and 4 right angles. When I say it's necessary and sufficient, I mean that it is, each one of these features are necessary. It needs to have 4 equal sides and 4 right angles in order to be a square. And those features, those attributes, are jointly sufficient. Any object with 4 equal sides and 4 right angles is classified as a square. So does that make sense? So they're necessary and sufficient. You need them, and that's all you need. It doesn't matter what material you're made of. It doesn't matter what color you're made of. It doesn't matter what size you are as a square. As long as you have 4 equal sides, 4 right angles, you are a square. And that's what the classically defined category model suggests. So once you know what those features are, whether it's kin relationships, quarters, or squares, you can classify things by applying the definition. This square is no good, no better or worse than any other square. If I made the square bigger, it wouldn't be a better square. If I made the square darker, it wouldn't be a better square. It would still just be a square. Does that make sense to everybody? If I were, if I made the quarter shinier, it's a better quarter. It's still a quarter. The problem with this particular approach is that for most of us, we overlook a lot of the variation. So this is where the idea of abstraction comes. We can agree that squares have a definition, but we're not really good at being precise. We can tell by looking at these squares side by side that they're not really identical. The one on the left violates the necessary and sufficient conditions. The one on the right really is a square. The one on the left is a little bit of a badly drawn square. You can sort of see where the lines don't quite meet. So one side is a little bit longer than the other. If I place one on top of it, you can see that the one on the left doesn't quite cover the one on the right. The one on the right is just a little bit crooked. It actually is a bad square. In fact, it's not even a square. We wouldn't usually go that far. We would be probably, most of us would be perfectly happy calling both of them squares, even though only one of them is. And that's one of the shortcomings of a definitional approach, is that unless we know how to apply the definition perfectly, it's not a really good model for how we do things. Even though we can agree there is a definition, the fact that we don't tend to use it suggests that we must be doing something else mentally. We can agree there's a definition here, and we can agree that one square follows that definition, the other one doesn't, but we can also agree that if we had to name them both, we would probably say square for both. So clearly we're aware of a definition, but we're not always using the definition. There's got to be something else that we use. And so that's one of the problems with the classical view. The problem with the classical view is that it's too strict. Even if we understand it, and even if we know that many concepts are defined by a set of necessary and sufficient conditions, we tend to view the world more probabilistically. A really good example, a philosopher in the middle of the 20th century, Ludwig Wittgenstein, whose work is going to come up again next week. We talk about language and concepts, because Wittgenstein was really interested in how we structure the world with language. Suggested that we do this with lots of concepts, and that most of our concepts, even if they have rules, we don't use them. And in fact, for most concepts, we don't even know what the rules are. In his written description, he describes something called a family resemblance. He suggests that consider what we call games. I mean, board games, card games, ball games, Olympic games, and so on. What's common to all of them? And so he asked this question about a lot of things. I mean, for anything that we have a label for, a name for, or a concept, what are the features that are common? We can list common features for games. But there isn't one thing that everything has. And that would be true for a lot of our concepts. There isn't one thing that all dogs have. There isn't one thing that all cats have. There isn't one thing that all university professors have. There isn't one thing that all squares have. Because if we're calling things squares that aren't perfect squares, there's something else. And so he's suggesting that most concepts, rather than having a set of rules or definitions, have an overall family resemblance structure. In other words, they resemble each other in a lot of ways, but they don't have one particular feature that's diagnostic. They don't have one or two things that is purely necessary and sufficient. They resemble, but they resemble as clusters. If you look, you will not see something common to all, but similarities, relationships, and a whole series. And Wittgenstein calls this family resemblance. And family resemblance is a much closer model for how we tend to form concepts. We can see this in a lot of different ways. So for example, this is similar to what we did, participants' typicality rating. So if I were to ask you, ask a group of subjects, and this is work that was done by Ellen Roche Associates. If I ask people to give a rating for what is the most typical, how typical is apple of fruit? we might give it a high rating. It's a really good example. And I think we agreed with that when we did the naming stuff, that it kind of seemed like it shared a lot of the features that other fruits have. It doesn't have one thing, but it shared a lot of things. You can see peach and pear and strawberry, blueberry, but by the time we get to avocado, pumpkin, and olive, they're less typical. They're still fruits, but they're less typical. They still have the definition, but we think that some of them are better examples. In other words, they have more of the family resemblance to other fruits. Same thing with birds. Robins are better birds and bluebirds and seagulls than albatross, penguin, and bat. Bat isn't even a bird, but it has a lot of features that birds have in the sense that it flies and does bird-like behaviors. So there's a typicality structure. This kind of typicality structure suggests that even when there's definitions, we overlook the definition or we add stuff to our concept that's non-definitional. Even in odd numbers, there's only one way to define an even number. It's a number that's divisible by 2, but participants tend to agree that some even numbers are better examples than others. If there's a rule for even number divided by 2, why should 4 be a better, more typical even number than 106? What makes 4 better than 106? Any thoughts?
Divide it by 2 once.
It's only divided by 2 once, but you could divide 106 by 2 once. And you would have 53. An odd number. That's a good try. It's got 2 in there. That's a better one. So it's divisible by 2 and the answer is 2. So that's a good example. Other reasons. So I like that one.
It's just like a smaller number, so it's like to the eye, it's easier.
It's just smaller. Maybe it's easier, and that's close to what you were saying too. So it's smaller. Maybe it's easier to mentally divide it by 2.
More common, like more available.
It's more available. That's definitely true because all the other numbers have every other even number has the number 2, 4, 6, or 8 in it, right? So 4 is one that is in all the other numbers. So maybe it seems it's kind of like the root of it.
Kind of like unspoken non-definition that some people follow by is that even numbers divide into even numbers, but 106 divides into an odd number.
So it's not as good. It doesn't even follow a good definition, even though there's only one definition. Maybe it's harder to sort of apply that definition.
Well, like when we're learning odd and even numbers, I feel like we usually do it between 1 and 10 at the start. So we're probably more familiar with like 4 and 8. So.
Yeah, it's just like I can tell the difference between even and odd numbers up to 10. And beyond that, I have to sort of think about it a little bit harder. So they're just recognized more quickly. So there are all of those reasons are potentially valid. Every reason that you gave, it's easier to do the math. The math does it into 2. It does it into an even number. It's a smaller number. It's more familiar because it's a number from 0 to 10. All sort of makes 4 seem better, even though you know deep down inside it is no better. It just seems more typical. It's more common. It's more familiar. It's easier to apply. And the same thing, of course, is true with odd numbers. It's an exact parallel. Small odd numbers are viewed as being better odd numbers than large odd numbers. In some ways, that's even weirder because there is no division even necessary. It doesn't end with an odd number, so therefore they should all be equally good odd numbers, but we still see the same typicality. So probabilistic views assume that even when there's a definition, but in a lot of cases, for a lot of categories, there isn't a definition, that things can be typical. There can be good, typical examples and less good, less typical examples. Category membership is not definite. A category has no defining properties, only characteristic ones. Dogs have characteristic properties, but no defining properties. DNA might not even be a clearly defining property. A couple of problems with DNA, you can't see it. All you can see are the characteristic properties that show up. And 2, there can be crossbreeding, which might suggest that even DNA might not be perfect. Genetic mutations might occur. If your dog has a genetic mutation, that means that it doesn't have the same DNA as another dog of the same species. It doesn't mean that one is no longer developed. It means that there's some overall family resemblance between them. Nothing is perfect, even genetic material is perfect. Category members share a family resemblance. And so the question is, and the last topic we want to cover today is, if category membership is not definite, and if category membership is somewhat probabilistic in nature, and if you're representing characteristic features, how do you represent those characteristic features? And we'll talk about two different approaches. One is the suggestion that you store for every concept and category, you only represent it with a single thing, a prototype, which would be an idea of what is most common. Or the alternative is you represent a category with lots of similar examples. The way to think about that is prototype for dog would be an image or a representation that's kind of the average dog. It keeps track of, or it represents the things that are most common to dogs. One single memory, one single idea. An exemplar representation suggests that your concept is the summation of all of the memories you have of dogs. So all of those things are combined and held together by similarity. For the most part, both of these models or theories kind of make the same predictions. There are a couple of cases where they don't make the same prediction. We'll talk about both of those. So let's talk about a prototype first. A prototype is thought to be an average. Prototype literally means the first type. How many of you have sort of an interest in engineering or inventing or computer programming, and you might think of prototyping? The prototyping means you create something first, and then you create other examples afterwards. So that's what prototype means, is that it's the first example. It's the first one listed. It's the one that has all of the features that everything else would have. It's the one that you start with. If you start with an example and then create other examples from it. In a family resemblance scenario, if you have a set of parents and their offspring resemble, the parents might be thought of as having the prototypical feature. Any object would be classified or identified because it shares more features with its prototype. So what is a prototype? So I want to talk about an experiment that was conducted. I think it was an experiment that was conducted in the late 1960s, but this kind of idea is still fairly usable. We even use this basic paradigm in my lab, even for some experiments we're doing right now. But let me show you sort of their original example. What Posner and Keel did in their original study is that they created a prototype object. An object with no name, no particular strong features. They just created an abstract object. And then they asked people to learn variations of that abstract object, to try to memorize it. So we're talking about birds and dogs. Imagine we create some new animal, some new object, and we start showing you examples of it. And eventually you come to understand what the common features are. If you'd never experienced a dog before, if you'd never experienced a cat, and somebody showed you a bunch of cats, you would quickly start to think, okay, well, I see what's going on here. All of these animals kind of act the same way. They look the same. You would start to appreciate what's generally true. That's what this experiment is supposed to cover. So let me show how it's designed, and then we'll go through a quick example of this study. So what I'm going to show you on the next slide, and I want you to pay attention to all of these. I'm going to show you about 20 shapes, one after the other. All I want you to do is to look at the shapes. You've got them on your slides as well, but look at the shapes and try to learn as many of them as possible. So I'm going to ask you to learn them, and then later we're going to do a task where you identify whether or not you've seen an object or not. So this is kind of a memory task, but it's also kind of a learning task. So you're just going to see objects on the screen. I'll just advance at a rate of roughly 1 per second. You ready? I hope this is an end soon. Okay, now there's a test phase. Everybody got that? I'll even show them to you again. Here they are in rapid succession. In fact, you can see them as rapidly as you want. And so you get the idea of what's going on. You probably have some idea of what this concept is going to be. And what we're going to do is on the next slide, this is the last QR code before we get to the last one. An exemplar test. We're going to see some shapes and you just say yes or no. Yes, I saw this. This is one of the kinds that I saw. Or no, this is not the kind of thing I saw. Wait just another minute. Okay. Is that? It's possible. I believe it. All right, let's take a look. We've got 82. I think there's a few more here, but if you haven't finished, go ahead. We can look at each one. So let's look over here at, let me close the other ones here. At the exemplar test, here is one of the objects you looked at. And almost everybody said yes. That is a shape, is a member of the category that you studied. Good job. Number 2, exemplar test number 2. Less certain on this one. So the first one, I think we all agree that looks really good. We got a high rating for this first object. For object number 2, we're kind of split. Most people say no, but a lot of people say yes. So on average, we're less confident about this one. Very confident about the first one, less confident about the next one. This one looks really good. I bet you this is one that looks like, there's the first one, there's the second one. All right, that one looks pretty good too. In fact, that one almost looks like the first one. And it looks like everybody said yes on that one. The next one, again, we're kind of split on this one. I'm less sure about this. It looks like something I saw, but it's less specific. Let's go to this last one here. And the last one, we're almost all, we flipped now. So some of them were really yes. Some of them were on the fence, and this one is really no. So I think what we can say is that we can agree that at least one of these shapes, 2 of these shapes, we're very confident that we saw. 2 of these shapes we're not sure, but maybe we saw. And one of these shapes we're definitely sure we did not see, because we all agreed it was a new item. Does that make sense? So what you've done is what's called a prototype abstraction task. Here's how Posner and Keel originally created the stimuli, and here's how I've used these in my lab as well. The reason it's called a prototype is that they would start before they did the experiment, they created the stimuli that you saw. They created the shapes that you saw. And they did that by just picking 9 spots on the screen, 9 pixels on the screen, and then connecting them. So you pick some 9 dots at random, 9 points on your screen in 2-dimensional space, 9 coordinates, connect those coordinates and draw a prototype item. From this prototype item, you can create lots of new shapes. And the way they did that was a very systematic algorithm. For some shapes, to create new shapes to see, they took the original configuration of dots, and each dot had a probability of moving a little bit. So in other words, you can imagine this shape here. Each one of these dots, if it moves just a little bit, the overall shape is going to change when you move each one of those dots, but it's going to kind of look the same. Does that make sense? So if you think about all of the dots just moving a little bit, the shape just kind of morphs a little bit. It's not a big morph, it's a little morph. That's what's known as low distortion, also high typicality.
Prototype always has to be shown first.
I'll get to that in a second. So the prototype is created by the experimenters first. It turns out the prototype is never viewed. So you didn't see the prototype. All you saw were distortions. So that's a great question. So the question was, is the prototype shown first? The answer is no, the prototype's not shown first. So we've created the prototype, but we're not going to show you the prototype. We'll show you the prototype later. So when we create these stimuli, we start with the prototype. It's the first one that makes it proto. It's the prototype. I then create new shapes by either moving the dots a little bit or by moving the dots a lot. So if the dots have a high probability of moving a lot, the shape changes more. So if you got one shape and you morph it a little bit, it looks a lot the same. And each time you start over again with the prototype and you morph it a little bit, you got a bunch of things that kind of look like the prototype. If you morph it a lot, you got a bunch of things that look less like the prototype, but sometimes, because this is random, because it's probabilistic, you'll get some shapes that do look a lot like the prototype because some of the dots stay in the same position, and you'll get some that look less like. So it's more variability. Does that make sense to everybody so far? So you got a bunch of shapes that are high distortions. They look less like the prototype, but they're still created from the original prototype. Now, if I took my original dots, erased them, started over again with a new completely configuration of 9 dots, I would have a new shape entirely. This new shape wouldn't be guaranteed to be the opposite or completely asimilar to what you've seen, but it's not going to be related to it. It's a new line. It's like a new creation. This is a new parent entirely. This is the parent. These are the low distortion children. These are the high distortion children, a little bit further. And this is a new parent. So this is a new category of shapes altogether. So that's what I've created. I've now created a prototype, a bunch of shapes that look like the prototype a lot, a bunch of shapes that look like the prototype less, but still are related, and some shapes that are not related at all. And then I show them to you. What you were trained on was a whole set of low typicality, high distortion items. So the items that you saw were from this group of high distortion items. In other words, you didn't see the prototype, you only saw high distortion items. Some of them looked prototype-like and others didn't. And then I tested you on prototype, high typicality, low typicality, and random items. And those are the things that you gave judgments on. So the question is, and this is what Posner and Keel assumed, is that if the prototype is abstracted, so if you see objects and you start to abstract a prototype, in other words, if your concept resembles the prototype, even though you've never seen it, it suggests that there's an abstraction process that looks for generalities. And that's what the data suggest. You should classify or recognize prototypes, even if you haven't seen them, more strongly than items that you did see. And that's essentially what your response showed. So the first item that you saw was a prototype. It wasn't the one that you saw during training. It looked a lot like everything you saw during training because it was the shape that created all of the things you saw during training. Does that make sense? So it's kind of like the center. When we talked about that false memory paradigm at the end of last week's class, the Deese, Roediger, and McDermott paradigm, remember those subjects were presented with words to learn, and the words were all centered around a gist word like sleep or anger or something like that. That's another way of thinking of this. This one shape is common to everything. And even though you didn't see it during the training phase, you would potentially abstract it. And then when you're classifying things, you might compare new objects. So a new object like this looks like the prototype. A new object like this looks a lot like the prototype. A new object like this looks a little bit like the prototype. And a new object like this doesn't look like the prototype at all. My microphone is on. Hold on. If I clip it to my shirt, to my quarter zip here. Try that. That's gotta be. I don't know. I don't know how to work these things either. If that's any better, I hope it is. Does that make sense to everybody? So you've now endorsed something that you haven't seen before. You've abstracted a prototype, and the fact that you've given it a high rating suggests that it is in your mind, even though you didn't experience it directly. So this is a hypothetical typicality gradient for the type of stimuli that you've seen. I've done these kinds of research. I've used this paradigm in research with humans, but I've also used this kind of paradigm in research with non-human primates. So we asked rhesus macaque monkeys to learn objects. They show exactly the same typicality gradient. So monkeys who have no idea what they're learning, all they see are shapes, and they respond to the shapes by pressing a joystick, moving a joystick to sort of advance the trial. They don't really have any idea what they're doing, and then they learn to respond to things that are related to the prototype. They show this same pattern. Chimpanzees show the same pattern. People with amnesia will show the same pattern even though they don't remember learning or being exposed to the objects initially, suggesting that the prototype abstraction process, we've done this with children as young as 3, this prototype abstraction process seems to be something fundamental about how we interact with objects. We abstract what's true, even if we don't have the ability to remember individual objects. Does that make sense to everyone? So, yes.
So, like the prototype view, kind of like a constructivist approach.
Yeah.
Building on to what we previously.
So yeah, that's a good way to think about it. So the prototype is constructivist in the sense that you're constructing a new representation. You're abstracting this prototype from your experience. And in this case, it's designed so that the one thing that's common to all of the objects you see is that original shape. You don't have to see the original shape, but if you see enough examples, the implication is that you have a representation in your mind that's like that original shape. So much so that when you see that original shape later, you would falsely recognize it, or you would strongly endorse it as being a category member, whether you're a human with amnesia, a young child, or a non-human primate. Probably other non-humans would do this as well, but I don't know that anybody's done prototype abstraction tasks with rats or pigeons, but rats and pigeons also show generalization to new stimuli in a way that would suggest they would learn prototypes too. Seems to be something about a fundamental law of abstraction. So how do we classify by prototypes or exemplars? So classification essentially assumes that you would classify by comparing new objects to a prototype. With the dot patterns, I suggested that if you've abstracted a prototype and you see a new shape, you compare it to what's in your memory, and if it's strongly like the prototype, you would strongly endorse it. And you can think about how this might apply to lots of different concepts. If you have a generic idea of what a dog is, dogs that are closer to that generic idea will be more strongly classified. Dogs that strongly resemble this generic dog would be identified more quickly. For dogs, most of us identify dogs pretty quickly anyway, but you could certainly imagine cases where a small hairless dog, for example, might be classified a little less quickly, especially if it's sitting right next to a small hairless cat, right? Then you're not sure which one's which. So you could probably imagine some boundary outlier cases, but for the most part, we classify dogs quickly, and we probably do that by accessing generic dog knowledge and not specific dog. So this prototype model, which I describe in the textbook, assumes that for any object, you might compare it to your mental representations, your prototype representations. Rather than comparing it to all of the objects you have in your memory, or rather than comparing it to a set of rules for what it means to be a dog, you just compare it to a general concept, an abstraction. And whichever abstraction it's closest to, probabilistically, is what you assume that you've classified it as. In other words, if the similarity to dog is fairly high, given its similarity to everything else, you would be more likely to classify it as a dog than a cat. That makes sense to everybody. So this equation here is just given the idea that it's a probabilistic decision. An exemplar model, this is the last model we're going to talk about today. An exemplar model is one that assumes that when you classify objects, you don't compare it to a general idea, you compare it to all of the ideas that you have. So instead of having a generic abstraction for what it means to be a dog, you have a lot of memories for dogs. Some of them are image-based, some of them are property-based, some of them are experience-based and functional-based. There might be some sound and smells that go with them, but they're all parts of your memories. And so when an object is encountered in the world and it is going to be classified or categorized or activating a concept, it does so not by activating an abstraction, but by activating a cluster of exemplars. Now, the difference between these two is that the prototype model assumes that you've forgotten a lot of information or you haven't stored it. You don't store individual examples. What you store is just the abstraction at the conceptual level. The exemplar model assumes that you store a lot of individual information, and then it summarizes in a way that's somewhat abstract to make the decision. Most of these models, these two models, tend to make the same kinds of predictions about how people classify things like dogs and shapes and dot patterns and so on. But there are some examples where these two models diverge and make differing predictions. So exemplar models account for a lot of the same things. And one of the ways in which they don't account for the same things is the idea of linear separability. This will be the last concept I introduce today. We are totally on track for completion. So linear separability is the idea that some concepts are fairly distinct from other concepts. So much so that you can almost draw a line through the stimulus space. Do you remember from a few lectures ago, from our lecture on similarity, we talked about multidimensional scaling. And we suggested that some concepts, you can think about them existing in a multidimensional psychological space. And we suggested that that could be 2 or 3 or 4 or multi-dimensions. No matter how many dimensions it is, there's probably a way to separate that space with a linear function. In 2-dimensional space, it would be by drawing a line. Everything on one side of the line belongs to one concept. Everything on the other side of the line belongs to another category and is represented with a different concept. Does that make sense to everybody? So that's the idea of linear separability. It seems like some categories are like that. Prototype models do really well at predicting linear separability. Exemplar models do pretty well also. But some concepts are not well defined with a linear function. In other words, we can't draw a line. There isn't a strict rule or a set of features that lets us separate the stimulus space. A prototype model, because it relies on a single abstraction, doesn't predict classification very well. And so the question is, if people can learn non-linearly separable categories, it suggests that they're not storing prototypes all the time. Let me go through a quick example, and then I think that's about it for the day. Any questions on this before I go on to the last example here?
Sorry.
Yeah.
Can you clarify, predicts a constraint? What does that mean?
So the constraint would be that if you only store prototypes, you would be unable to learn non-linearly separable categories. You would be constrained to view the world as linearly separable.
Can you repeat what you said with the non-linear again? Like it's not stored where?
Actually, the next example will probably show this a little bit better, but non-linear means that a category space can't be divided by a linear function, a rule, or a set of features. Let me show you on the example. I think this will help. I hope it will help. So imagine you got a set of objects. You live in a universe that only has 8 things. This is a very simplified universe. There are 8 things in your world. And your job is to learn how to classify these 8 things into 2 categories. So you now live in a world with 8 things and 2 concepts. It's a very simple world, but there are lots of ways we can divide this world up. That makes sense to everybody. Okay, so set of objects can be defined on 3 dimensions. So this is a 3-dimensional world. It is a world of shape, squares and triangles. It is a world of color, red and white. And it is a world of size, small and large. So you live in a 3-dimensional world of color, shape, and size, and your 3-dimensional world has 8 things in it. The simplified universe. Let's suppose that we take the same 3 objects and we just represent them now for our purposes of convenience in 3-dimensional space. There's no difference here. It's just that I've taken those 8 objects and I've put them in a 3-dimensional graph. Does that make sense to everybody? So we've got a shape dimension. Things are either squares or triangles. We've got a size dimension. Things are either large or small. And we've got a color dimension. Things are either white or red. And we can divide this universe up in lots of different ways. And if I wanted to teach an agent in this universe how to classify the world into 2 different groups, I could come up with lots of different 2-group configurations. For example, let's suppose that I wanted to teach a child in this 8-object 3-dimensional universe that these objects were called one thing, and these objects were labeled or categorized as another thing. So now there are only 2 concepts. There's the small concept and the big concept. If you had to learn to classify things in a traditional behavioral equivalence class, to choose one response for small things and another response for large things, you could do so by only paying attention to the size dimension. Does that make sense? It doesn't matter to you if these are squares or if they're red. All that matters is that some of them are small and some of them are large. So what that means is that you could divide this 3-dimensional space with a linear function by slicing it in half with a 2-dimensional plane. That's a linear function that essentially says, this is one idea and this is the other idea, and I don't care about the distinctions within this idea. I don't care if they're squares or triangles. I don't care if they're red or white. All I care about is this half of the world gets one label and this half of the world gets the other label. Does that make sense to everybody? That's a linearly separable category. If you're living in this linearly separable universe and you store prototypes, what would you store for this category? What would be your prototype?
Small.
Small. You would just have a generic idea of smallness. That would be your prototype. You would abstract the idea, a single idea, small things and large things. If you were an exemplar-based categorizer and you did not abstract, but you just stored everything with its label, what would you store? All 4 small things. Does that make sense to everybody? And your classification performance for both kinds of agents would be exactly the same. The guy over here who just stores small is going to perform exactly as well as the guy over here who stores 4 small things and the same label. So exemplar and prototype models make the same predictions for this linearly separable category. Okay, but that's a really simple linearly separable category. Suppose we now tell the agent that it needs to learn this object, this object, this object, and this object. Your prototype here, which we can also slide a 2-dimensional linear plane to slice the cube on an angle. I've done my best here with my limits of PowerPoint animation understanding, but you can see how I have sliced the cube in half with this guillotine here, so that everything on one side of the plane belongs to one category. And if I'm a prototype categorizer, if the agent that I've built learns how to categorize by abstracting a single thing, it would abstract small red square, because most things are small, 1, 2, 3 small things. Most things are red, 1, 2, 3 out of 4 red things, and most things are square, 3 out of 4 squares. Not a perfect rule. This is not a universe with a definition. This is a universe with a family resemblance. But if all I thought of was small red square, anytime I would see an object that had at least 2 of those features, in other words, the majority of its features in common with the small red square, I would correctly classify every single object in this universe without having to learn every individual object in the universe. I could just learn small red square. Does that make sense to everybody? So prototype learns this category really well, and exemplar model learns this category really well. Let's do one last example here. I've accidentally obliterated one of the axes. Suppose now I want to teach an agent to classify these things as belonging to the same category. Now my agent needs to learn 2 features that are important. Most of the things are red, so 3 out of 4 things are red, and 3 out of 4 things are square. So red is common to most, square is common to most, but 2 of them are small and 2 of them are large. So size is no longer a relevant dimension. If you pay attention to size in this categorization scheme, you'll be at 50%. So size is not relevant. Size does not correlate with category membership. So if you're a prototype-based categorizer, and if through trial by trial feedback, you learn to classify these things and you try to abstract what's common, what you would abstract is what's common, which is red square. What's the problem with red square? So my best attempt at categorizing or summarizing everything with a single object, red square, is going to result in suboptimal categorization. What would happen if I stored only red square and then try to categorize things by comparing them to the red square? Any guess?
Half of the things in red set are red squares. So you probably don't-
I'd be really good at the red squares because they would say, okay, it's red and it's square. I got most of my features. But if I've stored red square and I'm not paying attention to size, and I see this square here, it's got one of the features that I care about, but it has another feature that's common to the other prototype. So I would be 50%. So in other words, my prototype would be unable to classify all of the objects in the set. I've abstracted it because it's common, but when I try to use it, it's not very good. It only works for 2 of the items. It gives me chance performance. Some of these items, like this one here, share only half of its features with the prototype. It's square, but it's not the right color because size is irrelevant in this case. So what this implies is that a prototype is not useful for categorizing things that are not linearly separable. If, however, I stored the label with this object, this object, this object, and this object, which is I've stored individual exemplars, I would be able to classify all of these objects really quickly. You can certainly imagine that if I asked you, as a subject in an experiment, to learn how to classify these things, you wouldn't find this to be particularly difficult, right? You only have to learn 4 things as being classified as category 1, and the other 4 things as being classified as category 2. And you wouldn't be using a prototype. You'd likely be using individual exemplars. And so what this suggests is that for some categories, like really big ones that have features that are hard to describe verbally, and that have objects that look a lot like each other, like the dot patterns, maybe a prototype is an appropriate way to represent them. For other categories for which there's no linear structure, or for which a prototype doesn't classify things, we can easily switch to classifying things by storing individual exemplars. Prototype model cannot learn, and that's the constraint that I was talking about. So a prototype model can't learn non-linearly separable categories. Are there examples of linearly separable, non-linearly separable categories? LS just means linearly separable. So you might imagine that things like, mammals, for example, you've got lots of exceptions that don't seem to be linear. Mammals have lots of examples like bats and dolphins and whales, which seem to share a lot of features with other categories. We talked about small hairless dogs, which might share a lot of features with another category. Even the fruits that we did, we talked about how pumpkins might share a lot of features with something that isn't fruit-like. For lots of kinds of categories, natural concepts tend to be more likely to be naturally linearly separable. In other words, if there are joints, we tend to find them. Natural categories tend to be linearly separable, but for artifacts, this is showing a multidimensional scaling of things that are either toiletry gears or sewing gear. They don't tend to be linearly separable. There are lots of things which seem to cross over the rule, cross over the boundaries. So there are things, these are things which are nail polish, perfume, shampoo, etc. But some objects, which we would describe as being sewing related, kind of fit in there. And you can see why that might be the case. If you go to a hotel, you've got your toiletry items and there's always a little sewing kit there, right? Some of that stuff kind of seems like it fits into toiletry gear and vice versa. There are lots of examples of artifact categories which are not linearly separable. So this suggests we got a lot of flexibility in terms of how we store concepts. Which also implies that when we learn new concepts, we probably do a mixture of all of these things. That's what a lot of models would suggest. We learn things explicitly by trying to abstract the rules, but sometimes we just learn things implicitly, like we did with the dot pattern. We learn things by trying to find rules, but we also might pay attention to individual examples. Maybe we learn abstracted prototypes, but sometimes we learn specific exemplars for certain categories, and that we're using all of these things simultaneously. Okay, I think this could be my last slide. I hope it is. Okay, summary. Good. I've got one more slide about the exam, so don't pack up yet. And then I've got your usual foggiest concept. We represent our experience with concepts. We refer to concepts to make decisions, and features, concepts can represent lists of features. They can represent rules, individual memory examples, or abstracted prototypes. Okay, so I wanted to talk about the midterm briefly. I'm going to talk more about the midterm next week because midterm is in 2 weeks. Has everybody got that? So first of all, it's Tuesday, February 10th, 9:30 to 12:20 in this classroom. So we're just going to take it here. We've got enough room for almost everybody to spread out. There are about 280 students in this class, and the room fits about 480, I think. So there might be a couple of cases where you have to sit next to somebody, but generally speaking, you'll be able to spread out. Now, what I usually like to do is hand out the exams beforehand, but there is a class that finishes up at roughly the same time ours begins. I'll check with the instructor next week if they are giving a midterm at the same time, or if they're not going to be in this class, then that's great. I'll be able to get my proctors and TAs in here to set everything up ahead of time, but I don't think that's going to happen. So likely what will happen is we'll come in just like we normally do, and then we will work to hand stuff out as fast as possible. So that in 5 minutes, we should get everybody covered and you'll have an exam and an answer sheet. I've provided a study guide on Brightspace, which gives you a summary of what is almost certain to show up on the exams and leaves out a lot of the stuff which is less likely to show up on exam. It's not perfect. There are things that I'm going to ask you to study which might not be on the exam, or might be on the exam only tangentially. So I don't tell you which ones are going to be multiple choice, which ones are going to be short answer, but the study guide helps to consolidate things for you. The exam will be drawn from the concepts that are on that study guide. That means there are probably some things that are in the textbook that are not mentioned, which are very unlikely to show up on the exam other than maybe a single multiple choice question, which again will probably be one of those definitions. So use the study guide to help you focus on what you should pay most attention to. It's not perfect, but it's a really good example. I check that usually as I'm creating the exam to make sure there's a high correspondence or correlation between them. 2/3 of the points will be from multiple choice questions approximately. So that means that this is mostly a multiple choice exam. But the other 1/3 will come from written type questions. Some of those will be short answer questions where you have to write a few sentences. Others will be fill in the blank type questions where there is a definition and I'm just asking for the concept. So sometimes they're very similar to multiple choice questions, but I'm just asking you to recall the information rather than recognize it. So use the study guide. Assume that it's going to take you about 2 hours or more to finish the exam. If you take your exam with accommodations, it'll be there for you. And you would make those arrangements. I think you have to have 10 days, so it should be available pretty soon. I think there's about 60 some questions on there. It's maybe 80 points. I haven't created the final version yet. So that's why I said 2/3. Actually, the study guide might actually say. Let's quickly look at the study guide. I've got it over here, and you've got it, I think, also. Midterm exam preparation. Well, that's sort of hard. That's almost impossible to read. But if I make it bigger. Oh, there will be around 60 questions in total. And so this also gives you some general information about what you can do. So slightly more than half. I haven't picked the final questions yet, but this is usually what my midterm looks like. Slightly more than half, around 2/3 multiple choice, about 60 questions, and then just however many points it ends up being. And it's always going to be worth 40%, sorry, 42% of your final grade. For the midterm, depending on whether or not you're using the bright space, or not the grade scope sheets, you can use your pencil for that. But oftentimes the exam is going to be on on one single sheet where you'll circle the multiple choice rather than using the grade scope sheet. So bring pencils and paper. You can bring whatever else you want. When you come in, you can just keep your stuff with you. There's enough room to sort of spread out, so you don't need to leave your books at the front and so on. So take a look at this. Everything is in here. This is where we're going to be. This is what you need to know. I've sort of pointed out that you will be sitting wherever you need to sit. We'll just hand stuff out afterwards. And this sort of gives you an idea of what to study. Bold terms, and then these are some of the ways in which I've conceptualized stuff. This kind of overlaps with the way we've talked about it in class, and you'll probably notice there are some things that I've left out. A couple of quick summaries for some of the concepts. If you see there's a slide in there that isn't mentioned at all, it's unlikely to show up. Okay, last slide. Of course, you've got the usual. If you have anything you'd like me to explain next time, you've got this QR code on your slides. You've also got the link. Just let me know what you'd like to see. We'll talk about a little bit more stuff next week. Otherwise, enjoy the rest of the week today, and see you on the 3rd.
Oh, well. We sacrifice.
Well.